we will now solve a problem that we posed during the lecture. So we like to show that for time-like and light-like separated event, there exists a notion of Lorentz invariant time ordering for the appropriate choice of Lorentz transformation. Let's start to work it out. So we will start with the time-like case first. So let's consider the S frame. Consider two events A and B, and their space-time coordinates are I mean. Now we go to a prime frame where we become a prime, we become B prime. The corresponding coordinates are mu, pi prime mu. So what we have to show is that sine of x naught minus y naught. What this gives? This gives is the time interval between these two events equal to the sine of x prime naught minus y prime naught. As long as this A and B is separated by a time-like distance. So this means that when x naught is greater than y naught, that is A is in the future of B, it remains to be the same when we go to the S prime form, and vice versa. So let's try to show that. So we know how the Lorentz transformation acts on the position 4 vector. Remind ourselves, x prime lambda times x. So let's write it in the index notation. So we know that we can denote this by a column vector with 4 entries, x0, x1, x2, x3. So let's denote the indices called nu. So nu goes from 0, 1, 2, 3. And this is a column vector. So nu gives each of the row. Now this is written in terms of a matrix multiplication. So this is a metric, and so the column of lambda will be multiplied with the row. That is how you do metric. So as discussed, we will denote the upper index on lambda to denote its row, and the lower indices far away denotes column, right? And hence, of course, there will be mean index. Also, we know that in general, if you shift this coordinate by constant amount, adding a translation, that will also give the Minkowski line element invariant. This is the most general transformation. And here A is a constant for vector. Similarly, we can do it for y prime something new. So we will see that these constant shifts does not matter for our case, because anyway we will consider only the intervals. So take the difference between this mu, y mu, lambda. Sorry, there is a typo here. Y mu and we will focus on the 0, 0 component of this equation. So let's take the 0, 0 component, 0, 0, or just the 0 component. It's x prime 0, y prime 0, and so we'll have lambda 0 mu x mu. We know the repeated indices are summed over, So let's write this sum explicitly. So we divide it in the 0 and the special indices, which we denote by I, which takes 3 values discussed in the class. This is nothing but lambda 0, 0, 0, 0 plus 0 I psi yi. Now remember that for time-like separated event, we can always go to an initial reference frame such that the spatial interval vanishes. That is how we have defined the rest frame for this event. So if we do that, then we can set this term to be 0, and we have the following. 0, 0. Now remember that we have discussed two types of Lorentz transformation, orthochronous and non-orthochronous. Of course, non-orthochronous reverses the time direction. So we have to only consider orthogonal Lorentz transformation. We keep the time direction invariant. And for that, we know lambda 0 is greater than equal to +1. For ortho. And that's it. So if this is greater than equal to 0, that means some positive number is multiplying this thing. So if this is positive, so this will be positive. Okay. This is negative, so it will remain negative. So the sign of x prime 0 minus y prime 0 is same as the sign of x prime x0 minus y, and hence the proof. Now let's look at the null or light-like separate case. Okay. So one thing remember, for light-like separated case, we can go to a reference frame. It does not exist, because if you try to make dx the spatial interval 0, it will automatically imply gt to 0. Okay. But nonetheless, let's see how to prove this equivalence statement there. So we again start with this equation. Okay. Also remember g square 0 between two light-like separated event, and it follows from there that you can relate the time interval with the spatial interval, and without loss of generality, let's choose that it's not greater than. Why not? You could have chosen the opposite thing also. Right? We leave it for you to repeat this exercise for the opposite choice. Let's stick to this choice for now. And then, right, like this, we also know it's not. Why not? Will be mod of this. In general, this square is 0, which will give you both plus and minus and here, but we have chosen these two positive, so we have taken the plus. It is extremely important that we are going to, and this is the spatial interval. So this vector science is, this is like a 3 vector component. 1, 2, 3. Okay. Now construct 2 3 vector A and B. So this is just the usual 3 vector that you encounter in your Euclidean vector calculus, that is vector calculus in R3. And what are the components of this vector? So for A, the components are lambda 0 I. So this is nothing but these 3 real component of this particular elements of the Lorentz transformation. And for what are the B's? So the component of B's are nothing but, right, Y. And we know dot product of such vector is nothing but cos theta. And cos theta is minimum when it takes value -1. So this implies identity that A dot B is greater than equal to minus, it has to be equal to or greater than minimum value. Now let's put this vector into this and let's see what get. This side will have lambda 0 I times xi by I. Remember, this comes from this dot product, so repeated index is as summed over. So, and these are spatial indices. We'll see that within this context, if we raise and lower these spatial indices, there will be no sign change. So we are not very bothered about that. But we have to be very careful about the position of the 0 indices. It will be later clear on when we discuss more about the index notation. Anyway, let's proceed. On this side, we give you greater than equal to. So what is the mod of A? This is nothing but square of each of these lambda 0 i's, sum and then square root. So mod of A is square root of over I. I'm keeping the sum explicitly, but again to remind you that repeated index is summed over. And what are the, we just simply write it as this. Now we have this, and remember that we have this equation. We are going to replace this by this inequality, also replace this by this equality. So let's write this down once more. Yeah, x prime y and this will be replaced by mod of x minus y. And this we will want to replace by this inequality. So remember, this is greater than equal to this. So we'll have to change this equality to greater than equal to minus sum over I lambda 0 I square. This thing. And let's try to bring these two terms together. We'll have lambda 0 0 minus lambda y. This. Now let's try to do a bit more simplification. Let's look at the defining relation of Lorentz group, which is lambda t eta preserve the Minkowski metric, which we denote by eta. Eta is nothing but the 0 0 component of eta is -1. Then it's a diagonal matrix, so there's the identity 3 cross. Rest of the entries are 0. So now also eta square is what? So if you multiply this, you can see that eta square is identity. So eta is self-inverse. So now if you can manipulate this equation and get an equation for inverse, which is basically inverse lambda transpose times eta. Basically, you multiply this side by eta inverse and this side by lambda inverse, and you get this. Now, this equation says that the component of lambda inverse are related to the component of lambda transpose. So let's see schematically how they look like. Again, you can do it in the index notation very quickly, but just like what we have done in the class, we will do it in a brute force approach. Just to remind you, lambda, this we can see this component is the 0 0 component, because this is row index and this is the column index. This is the 0 I 0 and some block here, lambda ij block, don't care. And lambda transpose will be row column interchange is 0, and this block, whatever it is, transpose. Okay. Now if you multiply these two terms, then what we will get? Lambda 0 0 lambda I 0 I, and then this part times this diagonal matrix, which so first entries will be minus lambda 0 row column multiplication. These entries will be lambda I 0. This entry will be again of this, which is minus the I and something, if you don't care. And now finally we have eta inverse of this matrix of lambda t. So eta inverse is same as eta, which means I identity times this matrix. Let's write it down. Yeah. And if you do so, then you will see this element -1 lambda. So first element will be again lambda 0 0. Okay, because -1 is basically multiplying minus lambda 0 0, and there will be something here, something here, we don't care. But what about the elements here? So this will be this multiplying this column, nothing but minus lambda 0I. Now remember, this is equal to the lambda inverse. So lambda inverse, the elements again, we can parameterize as this is the 0 component of it, the 0I, the 0, and then something, some block. And just now what we get is the following lambda 0. Remember, we want to equate with this. So we have something here minus lambda 0I and this block. So if you compare these two, then you can see that 0 element of lambda inverse, nothing but 0, and this element minus of 0. We will see why we are doing this. Now recall that we have this inequality. Okay, let's rewrite it again. X prime naught minus y prime naught greater than equal to 0 minus now we can replace these by the elements of lambda inverse and these also sum of square of element of lambda. Let's do this. Inverse of 0. There is a minus sign that is dating these two, but we use square and sum of, so it doesn't matter. And square of it. Let me write it carefully here. Okay. Now this should ring a bell for you. Remember that inverse Lorentz transformation is also a Lorentz transformation. So it satisfies the same condition that it preserves the Minkowski metric eta. Now for the Lorentz transformation, we have shown in the class that if you compare the 0 component of both sides of this equation, you get a expression for lambda 0 in terms of square root of 1 plus lambda I0 square and sum of those terms, right? So similarly, we do that, take the 0 component, both side of this equation, 0. Will give that the lambda 0 equal to same relation for lambda elements of lambda. And why the plus sign? Because we are considering the orthogonal Lorentz transform. So now if you look it back, you can replace this lambda inverse here, and this will simply give the following: so x, y. And if you put it here, this term will cancel. So we will simply have and this is greater than equal to mod of this, which is a positive number in general, and hence the proof that for time like and like separated events, there exists a Lorentz invariant notion of time ordering when you are going from one inertial reference frame to another by a orthogonal Lorentz transform. Thank you for listening.